Okay, welcome everyone to today's UQM seminar. It's a great pleasure today to have Sri Raghu from Stanford, and he's going to tell us about the lattice duality web and manifestation of hidden symmetries. So I also want to mention before we get started that after today's talk, for those who have time and want to stick around, at some point we'll stop the recording and then we'll be able to hang out and chat for some informal discussion. And Sri can stick around after the talk, at least for a little bit. So looking forward to that. Okay, so Sri, you can go ahead.
Thank you very much, Mike, and all of you for being here. It's kind of, even though I know we're giving all these Zoom talks now, and it's not the best experience, it's still an honor for me to present a talk in front of such a, I don't get to give talks in front of such a refined group of physicists. So thank you for having me, and let's get started. So the work that I'm going to present is, let's see, I guess I have to just do it like this. Okay, was done in collaboration with these two brilliant guys. One is Jingyuan Chen, who was a postdoc at Stanford and is now a professor at the Institute for Advanced Study at Tsinghua. And a student at Stanford, Junho Son, with whom I've been working and who will be graduating in a year or so. Although these papers are a bit older, I wanted to give this talk because I think while some of you, or a sizable number of you, would have known about the first paper that's shown here. By the way, can you see my cursor? Anybody?
Yes, I
Okay,
can.
thank you. You may not have known the second one, and that's what I really want to focus on. So that's what I wanted to do. And the theme of my talk is thinking about dualities and using lattices as opposed to the continuum. Now you might say, why do that when you understand everything on the continuum already? That's a fair point you might make. I tend to come from a condensed matter physics background where I tend to want to frame things automatically and define theories in terms of the lattice. But in this particular context, I think the lattice versus continuum is a little subtle. The analogy that comes to mind is sort of like if you're interested in, the Olympics, like think of a marathon that you want to watch. The continuum is sort of like the award ceremony where you present the prizes to the winner and maybe a few runners up. But the lattice model might be like the event itself, where there's a fierce competition between various degrees of freedom, and not all of them survive to the end. But seeing how the interplay between the UV and the IR manifests itself, sometimes you realize the continuum limit, sometimes you don't. There's lots of non-universality, there's lots of universality, and all of that interplay I think is quite beautiful and sort of the essence of condensed matter physics. So that's the approach that I've taken. Okay, so for this expert audience, there's no background virtually needed, so that's a pleasure already. But let me just say, in case there might be a student or two who isn't familiar with this, ultimately these concepts of the 2+1 dimensional dualities go back, way back into the ancient era, I would say, where people, you can think of the equivalence of the Goldstone modes of a superfluid in 2+1 dimensions as a dual photon degree of freedom. I just got finished teaching from an arduous undergraduate electromagnetism class, and that's still festering in my head. So I would have probably framed it as, the density and the 3 current is the same number of degrees of freedom as, say, the 2 electric fields in the perpendicular magnetic field, like a 2D waveguide, the TE modes or whatever you call those things. So that underlies particle vortex duality. And then there's the other feature in 2+1 dimensions where you can convert statistics by adding a Chern-Simons gauge field to matter. And this is all well known from long time ago. So in recent years, these ideas were really crystallized quite beautifully by many of the people in this audience. And the idea is to say that these dualities are really just part of an entire web of dualities that are interconnected. And to go from one to the other, you can implement on a certain Lagrangian transformations known as modular transformations, two of which are shown here, which is one is known as T, which is taking a theory with some Lagrangian and having a background field a U1 background field, and adding just a simple level 1 Chern-Simons term for the background. So that's like adding a Landau level. Then there's this other transformation, which is more subtle, known as S, which is taking the background field and promoting it as a dynamical variable in the path integral. So this becomes little a, the dynamical variable I denote by little a, and adding this cross coupling between little a and the background. And one of the things that is subtle is, in addition to these transformations, one can also look at hidden transformations, hidden symmetries like time reversal, and they also lead to new dualities. And this was all really well presented in recent papers that in particular, the paper by shown down here by Seiberg, Sentil, Wang, Witten, and other papers as well. So just to give you a sense of part of this duality web, there's some old known results and some maybe less familiar aspects of this. So perhaps the oldest is the duality that was presented, that was studied by Peskin and Halperin and Dasgupta between just a 3D XY model and a gauged 3D XY model, known as the Abelian-Higgs model. Now, in addition to this, there are dualities like the XY model is dual to a fermion with a level -1 Chern-Simons term or level +1 Chern-Simons. And out here, I've just organized it slightly in this way such that you can see that a subset of the dualities can be related to other subsets through modular transformations. Up here, you see the XY model with a level 1 Chern-Simons is dual to either a free fermion or to a gauged fermion, QED3. And then these fermions in turn are dual to one another. This is the fermionic analog of particle vortex duality that was put forward by Sohn and studied extensively over the last few years. And finally, there's a duality between bosons and fermions. By the way, if there's any questions, please feel free to interrupt. So all of this was actively discussed 4 or 5 years ago. I'd like you to view my talk as largely an addendum to this discussion, and hopefully some new insights can come from it. All right, so here's what before I get into the details, let me make some qualitative remarks for those of you who are interested in maybe the big picture and not the details. We're going to be studying the dualities on a Euclidean lattice. So take a cubic lattice, for instance. Matter fields, this is just the usual thing with lattice gauge theories. Matter fields live on sites. Background and dynamical gauge fields will live on the links. And this is a Euclidean system, so there's space and imaginary time. You will see at times that there might be a temperature associated with this cubic system. That's really a fake temperature. It has nothing to do with, it's not really the temperature of the two-dimensional quantum mechanical system that lives in space. If anyone's confused about that comment, you can consult the book by Subir, and he explains it at several points clearly. The next thing I want to say is on the lattice, we want to represent, say, the Wilson-Fisher fixed point in 3 dimensions for just O2 will be the only thing I'll be thinking about here. And as many condensed matter physicists know intimately well, this is captured by having rotor variables, angles on each lattice site coupled by Josephson coupling, known as the 3D XY model. And this lattice model can, in certain instances, flow to the Wilson-Fisher fixed point as you coarse grain. Then, in order to implement Chern-Simons theories, Chern-Simon fields, and preserve gauge invariance and compactness and stuff like that, not only Chern-Simons, but also these modular transformations, as you'll see, which will be related to making a web accessible on the lattice, we will implement these things via fermions. Okay, so now it's extremely well familiar to even the random condensed matter physicists on the street that a Dirac fermion, an even number of flavors, say in some lattice model with the partner fermions and so on, in certain circumstances gives rise to a level 1 Chern-Simons theory. So you can implement Chern-Simons simply by adding Dirac fermions on the lattice. Okay, so this is the essence. And then with these 3 building blocks, it becomes a game of making Legos, if you wish, just putting it together in different contexts. Okay. And one of the goals I'd like to have in this talk is how certain hidden symmetries become manifest in such lattice constructions. So the first thing I want to talk about, and I'll do this relatively briefly, is the lattice boson fermion duality. I'll do this briefly because it will be mainly used as a tool for later on. So as I said, you start with the 3D XY model, which flows to the Wilson-Fisher fixed point in the continuum. And the partition function is written in this way. So there's some angular variables, and this is just the usual 3D XY model. Now, as we teach in statistical mechanics classes, you can recast this in the so-called current representation, just Fourier transforming each link, and using the idea that this exponential can be written in terms of an infinite series of involving modified Bessel functions. And these little j's are currents, the boson currents. And it doesn't matter, the details don't really matter much, but for us here, but think of this as just a hopping representation in which bosons are hopping on this Euclidean lattice with hopping matrix elements given by these Bessel functions. And since they're bosons, you can hop as many of them as you want at any given time. So the currents can be any integer value from 0 to plus or minus infinity on each link. And of course, if you integrate out the angles, you'll get that these currents are conserved, which is just a restatement of the original charge conservation. The other thing is, if you want, now we want to implement Chern-Simons. So I'm going to define another partition function, which has 2 parameters, a mass and some interaction, which will play a minor role in this talk. And it involves 2-component Dirac fermions on the lattice, the kind that was studied by Wilson in lattice gauge theory, but now in 3 space-time dimensions. And the lattice model has a mass term and some hopping-like terms and interactions. Okay, so what you need to know is that if the interactions for the moment are switched off, the fermion masses generically lead to a gap system, except at some isolated values of the mass. Say for 1 and 3, the mass gap closes. But otherwise, the Lagrangian, if you integrate out the fermions, will be the leading order term will be a Chern-Simons term plus all the infinite tower of irrelevant operators. And this level C is given as, it just depends on the mass. And it can be 0 when m is greater than 3. This is all for u equals 0. In this range between 1 and 3, it's 1, and -2 for m less than 1, which will be of no concern to us. Here, you can look at effects of weak interactions on the phase diagram at u equals 0, and that can be worked out perturbatively over here. So there's a phase transition between level 1 and 0 at m equals 3 in the non-interacting limit. The other thing is, the fermion, being Grassmann fields, you can expand the partition function exactly. And it's akin to the sort of high temperature expansions that we study in statistical mechanics. When you expand the partition functions, you can have currents between bonds, either going to the right, going to the left. There could be an interaction term, which I denote like this. This is a net 0 current term. But the important thing is that the expansion can be done exactly because of the Grassmann algebra. So when you expand the exponential, you get a 1 and you get some term linear in the fields. The quadratic part goes away because of the Grassmann algebra. And another important thing to note is that this expansion only results in closed loops of these fermion currents, okay? Unless you're interested in the 2-point function, open paths like this are forbidden, okay? And that just comes from the fact that the integral of d chi is 0, okay? The Grassmann, basically constraints from the Grassmann algebra. So what this tells us is that while the bosons can hop as many, you can hop as many bosons at once on a link as possible, fermions you can only hop in, and the currents can only be plus or minus 1 or 0. But again, the currents are conserved. Okay, so in order to establish a lattice boson fermion duality, what you do is you say, I want to have a lattice realization of the 3D Wilson-Fisher plus level 1 Chern-Simons. This is a level plus 1. That's just a dash. So what you do is you write down the XY model. You couple this to a dynamical gauge field, which I denote little b, and you add a partition function for these massive Wilson fermions that couple to both a background field A and B, as follows. And now the thing you can do is, since the gauge fields live just on the unit circle, you can integrate out little b exactly. And what that does is essentially glues the fermion, the Wilson fermion, to the rotor fields, the boson field. Okay, and so when you do this, you get a new field psi, which I denote schematically here as the original fermion chi times e to the I theta, the XY model angle variable. And its partition function is up to a constant, which involves these Bessel functions and is unimportant, just another version of a lattice Wilson fermion, but with renormalized masses and renormalized interactions, whose values are exactly known over here. Okay, so you can view this in several ways. You can set u equals u prime. In that case, m prime would be equal to m. And this is just a familiar realization of parton theories, where, you know, if you have you can write a new fermion in terms of the product of the boson times another fermion. Another way to view this is to set the interaction u equals 0, and then you ask, when will this mass m prime cross 3, or in the neighborhood of 3? Since m prime is m times the square root of 1 plus u, and that's bigger than 1, if the original mass is just a little bit to the left of 3, the renormalized mass of psi will hit the critical point first. So what that effectively realizes is a light Dirac fermion, okay, of psi, but in the original boson side, it would be a XY model coupled to a massive fermion, which produces a level 1 Chern-Simons. So that's how you see the boson fermion duality on the lattice. Okay. Are there any questions about this? I kind of went through it quickly. I just, you know.
Yeah, I'm really confused. What are the global symmetries of this system?
Okay, sorry, let me try to go back.
You said you were not planning to go back, so I waited for a point to ask the question.
Oh, okay.
No, but I'm serious.
Of the XY model?
So on one side, you have the XY model,
yeah,
coupled to a gauge field with Chern-Simons term.
Yeah.
And that has, what's the global symmetry?
There's a U1.
And that is whose current is F?
Whose current is F. So, okay. Sorry, unfortunately, I can't scroll back. Sorry. Oh, now I can go back. Okay, good. So here, okay. The XY model is actually, the current has been, it's a gauged XY model, right? And that gauge field has a level 1 Chern-Simons.
Okay.
Okay. And on the free side, on the fermion side, the new fermion field is just a product of the field that produces the Chern-Simons term, which I denote chi, and the boson field, e to the I theta. It's the product of the two.
Right.
Okay.
So in the end of the day, you have only one global U1, which is coupled to A.
Yes.
And microscopically, what
Yes.
does this A is like a magnetic coupling of little b?
No, it's like a magnetic coupling of little b.
Let me ask it differently.
Yeah.
You have a dynamical gauge field B.
Yeah.
It's a compact U1 gauge field.
Right.
Do you not include monopole operators for little b in your Lagrangian?
Well, the path integral is over a circle, so they're automatically present in the path integral.
But then you don't have the global U1 symmetry.
The global, well, I mean, okay, so.
Imagine we had only B.
Yeah.
Raise everything else.
Yeah.
Is there a global U1 symmetry associated with the magnetic flux of B or not? Is this a global symmetry of the system or not?
That's not manifest in the partition function, at least. So.
But isn't that what big A couples to?
Pardon?
Isn't that what big A couples to?
No, big A, okay, so in this microscopic model, lattice model, the big A simply couples to the Dirac fermions on the lattice. Okay, and if you can think of those fermions as sort of imparting flux onto the bosons, and they couple to the background field, but the boson itself doesn't. So I agree with you that there is no global U1 symmetry in that sense, but the lattice model is perfectly well defined.
Okay, go on.
Okay.
Shri, one more quick question.
Yeah.
So if you set U prime and U both to 0,
yeah,
do you somehow run into trouble then?
Well, then you cannot establish the duality, because then both the when both fermions are critical at the same point, then you can't say that it's more then. Okay, so if you did that, the critical point, if U prime and U were both 0, or in general, if they were both equal to one another, the critical point would occur at this temperature T, this fake temperature equals 0. That's the only time when you can satisfy this inequality.
And that's somehow singular, is that right?
I mean, it's some fine-tuned point. I never, yeah, it is. I guess it is kind of singular, but generically, what you can say is M and M prime will go cross 3 at different values, right? And then you have both sides of the duality established.
Mm-hmm. Great, thank you.
Mm-hmm. Can I ask a question?
Sure.
So the first line is there are no fermions there, it's just the Chern-Simons and mutual Chern-Simons.
Which first line? Over here?
Yes.
This thing here, the partition function, which in the IR will implement a Chern-Simons term for the boson, is cast in terms of Dirac fermions. So these are fermions.
So it's minimally coupled fermions. They minimally coupled to B, and then B has a...
They're coupled to B and big A. So this is what the coupling is to.
Right, and then that gives you a mixed Chern-Simons between A and B?
It gives you a Chern-Simons for A minus B.
A minus B, I see. And so when you say then boson gets glued to chi,
yeah.
I'm trying to understand what that actually means. Like, okay, physically, what does it mean at the level of sort of operators? There's some operator that...
Yeah. So as I said, so bosons on their own would be hopping. You can hop as many bosons as you possibly can. Fermions, you can only hop 0 or plus or minus 1. When you integrate out little b, you can only hop plus or minus 1 bosons or no bosons. So the boson currents get completely constrained to that of the fermions. So the boson current equals the fermion current. That's the sense in which I mean that the fermion is glued to the boson.
Mm-hmm. Okay, thanks.
And you can see this explicitly on the lattice just by expanding out the Grassmann algebra and integrating. It's an elementary integral of b, since it's just on the unit circle.
Mm-hmm.
Okay,
Thanks.
All right, so now I want to move on and use this to talk about the other dualities on the web, in this web. So, I talked about S and T, but what is more useful in retrospect, if you look in the literature, and also for me, will be these linear combinations, these new transformations, T, S inverse T, and its inverse. And so, for instance, this first transformation takes the Lagrangian, promotes the background field to a dynamical gauge field, and then adds a Chern-Simons for A minus big A. Okay, and of course, this is just the inverse of this. So this operation, in addition to just T, will generate the entire web. So that's sufficient. So I'm going to work with these. Now, since the Chern-Simons term like this can be implemented with fermions, that is how we will obtain the web of dualities on the lattice. Okay, so these transformations form the group of SL2Z. So obviously, if you impart with one operation and you undo it, you must come back to where you started, right? So if you take this Lagrangian and act on it with this, you get this new theory, but then doing this undoes it and takes you back to the original Lagrangian. And that's sort of obvious in the continuum, but it's not so obvious in the lattice. In fact, in general, this is not going to be true. So what happens is, as you'll remember, for those of you who don't know this, let me remind you, let me say how this works. It actually sort of works in two steps. If you take the original Lagrangian and you operate with this modular transformation, you get this new theory, as I just mentioned. Now, if I undo this transformation, I'm actually going to introduce a second gauge field, a second dynamical gauge field B, which I call B. And so now there's a whole bunch of new gauge fields and this Lagrangian. How do you get back to where you started? You note that little b doesn't couple to the matter fields in L, and it can formally be integrated out. And you see that since little b only couples linear, it's only entering linearly, it acts like a Lagrange multiplier, implementing a Dirac delta function constraint on little a minus big A. And that's how you get back to where you started.
I'm sorry that I still have to ask the same question I asked.
Yeah. Yeah, I'm not sure I answered your question, actually.
Well, maybe you did, but I didn't understand it. The manipulations on this slide, which I think I understand, I understand what it means in continuum field theory.
Yeah.
But if you try to put it on the lattice,
exactly.
Especially if you say that the lattice includes the monopole operators for all the dynamical fields, then it's not clear to me that you can really do it. So for example, just looking very superficially, you could integrate out little b because it appeared quadratically in the Lagrangian. Right. But on the lattice, does not appear quadratically, so it's not integrated out so easily.
Absolutely. That's exactly what I'm getting to next. So maybe this will answer your question. So now let's try to do this on the lattice, exactly as you said. Okay, so instead of a continuum Lagrangian, I'll have some path integral, some partition function, z of a, and its particular nature is not so important at this point in time. We're going to act on this partition function with this modular transformation. Then what will happen is that we'll have a new theory where we introduced a dynamical gauge field, little a. The partition function now couples to this dynamical gauge field. And then the Chern-Simons term implemented here will be through the form of fermions. Okay, so that's what this Z sub m is. And the fermion, Dirac fermions couple to the combination of little a minus big A. Good. So now if you act on it with this the purported inverse transformation, you'll get a new partition function, which involves now a path integral with two dynamical fields, the original partition function, and now two of these Wilson fermions with different masses, m and m prime. And now how are you going to get back to where you started? Well, in general, as Nadi says, it's not always going to happen on the lattice. So what you need to do is the following. If you look at the part that only involves little b, so again, the original partition function, which I denote z, is coupled to a dynamical field A. But if you look at the part that involves the dynamical field B, it involves this partition function, these two fermionic partition functions. And so the only way you can get back to where you started is if the fermions under some range of parameters form a superconductor. So that there's a Meissner effect. Once you integrate over little b, there's going to be a Meissner effect for the combination of little a minus big A. So that would be the lattice analog of the Dirac delta function constraint. So it's sort of softened by the Meissner effect. But as you go to lower and lower energies, the constraint becomes harder and more like that of the Lagrange multiplier. So that's what you expect to happen. But in general, this is not going to happen with these fermions. They're just some random fermions. They're gapped. Who's to say whether they'll superconduct or not? So for that, we actually looked at this from the lattice model and did numerics to see if indeed this combination of big A minus little a is Higgsed. So let me just tell you what we did. In this functional integral, you can actually do the integral over little b exactly, okay, without any numerics. And you get some, you represent these partition functions in terms of Dirac fermions. Notice the importance of the complex conjugation here. In this theory, the complex conjugation came because we had the opposite sign of the opposite level of the Chern-Simons term. So the Dirac fermion is complex conjugated for that reason. And that's going to be extremely important. Okay, so you expand out the Grassmann algebra, you integrate over the dynamical gauge fields exactly, and then you say, let's see if I can simulate the resulting fermionic theory using quantum Monte Carlo. And again, you cannot in general do that unless when the masses m and m prime are the same, so that there's a time reversal symmetry. And also if you set the combination, these gauge fields, little a and big A equal to 0. Okay, so that's a huge caveat that I'm laying out there. If you go ahead and do that, what you'll notice is that there is indeed a fermion which is charged +1 under big A and charged -1 under little a, which superconducts, okay, for a range of masses when they're equal to one another. And the evidence for superconductivity can come from looking at the pair field superconducting correlation function as a function of, say, one of the distances on the lattice. And you can see that for some range of masses, the correlations decay exponentially, whereas for other ranges of other values of the masses, the correlations are long-ranged, indicating superconducting order. And so, at least for this particular problem, you see that there is a phase, a range of masses. You don't have to fine-tune these masses, but there's at least a range where these fermions from these two partition functions would superconduct and Higgs out the combination of big A minus little a. And there's a range where they don't. And then you cannot say make this claim. Okay, so now, we did a rather huge deformation. We set little a to 0, which you can't really do. So the hope is that in this superconducting phase, at least for small values of big A minus little a, you would Higgs out this combination, and then that in turn would give you a way of going forward one link on the web with this modular transformation and coming back to where you started. So it wouldn't be much of a web if you can't come back to where you started. And so this is at least a proof of concept that there's a range without fine tuning. You can impart these modular transformations. So Nadi, does that help with the issue, or is there?
Well, here I'm actually still puzzled, because the spirit of the previous slide is that you wanted to write a Chern-Simons term on the lattice, and that's not so easy. So you say, I'm not going to do that, but instead I'm going to add a massive fermion.
The massive fermion is the Chern-Simons.
The previous slide was a proxy for the Chern-Simons term.
Yeah.
But on this slide, m actually has to be small, because you would like to use some dynamics of the fermions.
It has to be in some range.
Some range, but in the previous slide, m could have been taken. In fact, the spirit of the slide is that m is infinitely heavy.
Yeah.
So you're not in the same regime.
Yeah. So the you have to look at scales, energy. You have to probe the theory at energy scale small compared to m, and then actually it's m-3, the deviation from the critical point, and then you see that this continuum intuition starts setting in on the lattice. Okay. But otherwise it doesn't.
Still not clear to me is is the role of monopole operators for any of these gauge fields. And they are in danger of messing it up. And for some reason, I don't see it here.
Hmm.
The reason I
I'll have to
ask
think
is that
about that.
whenever I always give talks to condensed matter people, I always get in return, oh, but you have to add the monopole operators because in 3 dimensions we have Polyakov mechanism and so forth.
Yeah.
What that thing does is to mess up such simple manipulation.
Yeah. Sure. Yeah, that's something that requires some thought. But the fact that, you know, numerically, I can show you that there's a Higgsing of this combination is at least a proof of concept that you know, the confinement that you're thinking of isn't happening.
Sri, could I ask a question?
Yeah.
So when you say you find a superconductor, are you looking for the for the pairing function of chi, or are you condensing B? Which object condenses?
So there's 2 fermions here, okay? One that couples to this combination and one which couples to this combination.
Yep.
Okay? Let's call this chi1 and chi2. The combination of fermions that condenses is a bilinear of chi1 and chi2, which is got charge 1 of the background field A and charge -1 of little a. And so when they superconduct, they expel, there's a Meissner effect of this combination of fields. Okay?
I see. And then so is there a way to try to answer Nadia's question by asking, if you have a proliferation of monopoles of B, what would that do to your superconductor?
Well, I mean, we integrated out B exactly. So that's the part I don't really know how to address.
Right, but you
first integrate out B exactly, and then you do the numerical simulation.
Oh, so you're not sampling B, you're not actually sampling.
No, you're not sampling B. You've in fact solved the path integral exactly for B.
I see. So then in terms of your Monte Carlo, the sine-free Monte Carlo, what you're actually simulating is 2 copies of chi, this chi1 and chi2, correct?
Correct.
And the only thing they couple to is little a and capital A. B
Correct.
is gone by the time you do the Monte Carlo.
Correct, exactly. Correct.
Does B have a kinetic term in the lattice or not?
Little b?
Yeah, the plaquette terms.
Yeah, so actually the only way they enter is through Peierls phases, just e to the I b times lattice links and stuff like that.
Right, but when you wrote this, when you said that you integrate out little b exactly,
yeah,
does your action include, or doesn't it include a
Maxwell term, you mean?
Sorry?
You mean like a Maxwell term for it?
Yeah, Maxwell in the continuum and plaquette term.
Yeah, so you can include it. This particular numerics did not include a Maxwell term for B. We found that when you include the Maxwell term, it makes finite size effects worse. And so I don't know the definitive answer in that case, but this particular case does not include a Maxwell term.
I see. So you're a strong coupling as far as the gauge coupling is concerned.
Yes, yes.
Shri?
Yes.
Could you flash the assignments of Chern number as a function of M again, or maybe?
Yes, of course. Let's just. The hardest challenge for me is somehow to scroll back. Okay, so is this the one? Yeah, over here, Max.
Ah, I see. Okay. So for very large M, it's actually C equals 0.
Yeah.
Thank you.
How am I doing with time? Oh, okay. Looks like I'm already way over my. That's good. There was lots of good discussion. So let me.
You still have some time though, Sri. I mean, we started a couple minutes late, and
okay.
You have at least 5 minutes, but I don't want you to rush and compress a lot of things into 5 minutes.
Okay, no, that's fine.
Really
I want to give more of a flavor. So this is important for me because this emboldens me to say now that I know there's a range of masses of these heavy fermions or massive fermions that I used for Chern-Simons, they can actually, there's a notion in which the modular transformations are invertible, at least over some range. I can now do the following. So we started with this duality where the boson plus level 1 Chern-Simons term is dual to a free fermion as implemented on the lattice. Now we can quote unquote move this Chern-Simons term to the fermion side. And to do that, we impart with on both sides with this T inverse ST inverse. So when you do it on the boson side, again, we're going to get two copies of this massive fermions. Notice that it's Z times the conjugate of Z, and that's important. That's what enables them to superconduct. If there was no conjugation here, the attractive interaction becomes a repulsive interaction, and they don't superconduct. And I think for those of you who are familiar with who wrote papers on the duality web, I think that will make a lot of sense to you. So anyway, when you look at this combination will Higgs out when you integrate over little a, that will Higgs out little b minus big A, and that takes you back to the original boson. Okay, but on the other hand, if you look at it on the fermion side, there's no sense in which anything gets Higgsed out. At least you can view this as one fermion, which will become the light fermion. Okay, and a second fermion, which comes from this modular transformation, which imparts a level -1 Chern-Simons term for little a minus big A. So that's the sense in which this duality between a boson and a fermion with level -1 is imparted on the lattice, or is captured on the lattice. Now, let me make a few other comments. Let me at least get to this part before I wrap up. So this particular duality is quite interesting because one side has just an XY model, and the other side has fermions with Chern-Simons. So this model manifestly preserves time reversal, but the fermion theory seems to break time reversal due to the presence of the Chern-Simons term. And this was, of course, discussed at length in these beautiful papers. The resolution is that the fermion is dual to its time reversed partner. Okay, and heuristically, what that is under time reversal, the boson theory is invariant, but these fermions, which are composites of the boson and the vortex, are not. So they get transformed under time reversal so the vortex becomes an anti-vortex, and so this is a different fermion in principle. So this was known from older papers. What I want to now ask is, how do I think of this? How do I construe this on the lattice? And the way to do this is, again, to go back to this very elementary step, which is to take a modular transformation and its inverse. And when you act on it with this 3D XY model, you should get a new theory, which is, while different, it has other degrees of freedom. In the infrared, it should flow to the same fixed point, namely that of the 3D XY model, the Wilson-Fisher fixed point. But now on the right-hand side, when you do this, on the lattice model, the partition functions have two additional dynamical gauge fields, and the original XY model, which is now gauged, and a fermion, which was used to impart this modular transformation, and the second fermion, which was used to impart the inverse. And there's three ways to view this, this theory. The first is to say, integrate out little a. Okay, again, you can do this exactly on the lattice. And what that does is it Higgses out the combination of B minus big A. And that results in just the 3D XY model. The second viewpoint is to integrate out B. And again, that can be done exactly. And what that will do is it glues the first fermion to the XY model, the rotors, and that can be viewed as another fermion coupled to a level -1 Chern-Simons gauge field from this massive fermion. But now, how do I manifest the other fermion theory, the time-reversed fermion? The way you do that is you make a simple, or rather trivial transformation on these gauge fields. Okay, just introduce a field A prime, which is some linear combination of A, B, and capital A. When you do that, you get this functional integral, which is now, notice that the XY model couples to little b, and the second fermion couples to little b as well. But it's a sort of time-reversed fermion, okay? And now what we can do is integrate out little b exactly, and that will glue the second fermion to the boson. And in the end, what happens is this is the time reverse fermion, because if you compare the original fermion, which had a partition function z, this time reversed fermion has a partition function of the complex conjugate of z. It also couples to the opposite sign with minus a prime, but this system has charge conjugation, so you can undo that by charge conjugation. And so this is a time reverse fermion, which is now coupled to a level 1 Chern-Simons term. So at the end of the day, you can implement over a certain range of these mass terms on the lattice this hidden time reversal symmetry between the Wilson-Fisher fixed point, or the 3DXY model, between these two sets of fermions. Okay, one which is, both of which are time reversal, are related via time reversal with respect to one another. All right, so I'm more or less done. Let me just say that, to capture the fermion vortex duality, I'm not going to say anything new right now. You simply take this fermion and time reverse fermion duality, this was already observed in this paper, act on it with this modular transformation, and you will recover the duality between QED3 and the free fermion. That can also be done on the lattice as in similar spirit. Okay, I'm more or less done. I'll just say, we also looked at n=2 and self-dualities and stuff, but I've sort of forgotten the details. It's in this paper. I didn't have the time to look that up yet again, but we can discuss it at some point. I think I'll stop here and take questions.
Great. Let's all start by thanking Sri for a nice talk. So before I stop the recording, we have time for some questions, and then after the question period, we can see if people want to stick around and chat informally.
Quick question, Sri.
Mm-hmm.
So am I correct to say that none of the theories you considered have a true time reversal symmetry on the lattice? Including the free fermion?
Let's see. Well, okay. What do you mean by true? You mean microscopic time reversal symmetry?
Yeah.
Yeah, I would say that's true. I would agree with that statement. I will say this, Max, that if you look at these two theories at scales big compared to the fermion masses, then they don't look time reversal invariant. But if you look at them at scales small compared to the masses, where the fermions would have decoupled except for leaving behind some lingering Chern-Simons terms and so on, then there is a time reversal symmetry between the two theories. Mm-hmm. So in that sense, actually, the lattice constructions show they don't make these dualities exact at the lattice scale. They, if anything, strengthen the notion that these dualities are really infrared dualities.
Well, I guess your first duality was at the lattice scale.
Pardon?
I guess your first duality was really at the lattice scale. The one.
No, I mean well.
You had some relation between M and M prime and U prime, and
yeah, that's true. Well, you know how the degrees of the coupling constants match with respect to one another. That doesn't mean that the theory is really at the same fixed point on both sides, right? These two partition functions, they require certain finessing of the mass terms and so on. And so I would still characterize this as an IR duality, but I don't know. Now we're getting into the philosophical. I think we should ask. Is Sentil still here? Maybe he has an opinion. Maybe he left. Yeah. So that's what I would say about that comment, Max.
Mm-hmm. Thank you.
Do we have some other questions?
Yeah, since Senthil is not here, I might say something about duality. I'm not quite sure what you mean by exact duality versus infrared duality, in the sense that you wrote some lattice model and it is the same as another lattice model. That's an exact duality. It could be an infrared duality if you compare it to the continuum models. So you don't start literally from the model that you wrote, but from something else. So the models that you wrote, you claim that you took a model and you manipulated it correctly on the lattice and it was the same as another model. So I don't see in what sense this is an infrared duality. What is an infrared phenomenon is that you have an emergent symmetry in the infrared, as Max said, which is not present on the lattice. This is an infrared fact.
Yeah.
But the way you phrased it, the duality is exact. The infrared duality in this story is that if you write two continuum Lagrangians, which are clearly different, and they both flow to the same infrared point. The analogous thing for you would be to change your lattice models, so the two sides of the duality, by some irrelevant operators, such that they still flow to the same point. Then the duality would be infrared duality.
Yeah, I mean, I take what I meant was, take the XY model and the fermion on the lattice. Yes, there's a set of manipulations that make one partition function equivalent to the other. But I refrain from thinking of this XY models, is it a boson? Is it a fermion? It's not manifest. It's only true at length scales, or energy small compared to the Dirac fermion mass, where you can make sharp statements about that, right?
I don't understand what you said. There are two lattice models which you claim are the same. There was no infrared limit or anything. You just claimed
I think we're saying similar things, perhaps slightly differently. I'm saying that if you want to ask about low energy properties in terms of what the degrees of freedom are, what their nature is, then you have to, look at length scales or at energy scales small compared to the characteristic scales in the partition. You have to do effective field theory on this partition function. But yes, there are some exact set of manipulations which may or may not be useful, but they are exact on the lattice scale. Certainly, the time reversal symmetry is not an exact symmetry, as Max says, only true in the deep infrared.
All right. If there are no more questions, then why don't we thank Sri again?
Thank you.
Thanks. And we can go ahead and stop the recording.